Today we are starting notes on chapter 4, so this is our first note sheet. And so we're going to be covering a quick unit on early atomic theory. So we're going to recover what subatomic particles are and what they make up, and then talk a little bit more about how atoms were discovered, how subatomic particles were discovered. And yeah, it'll lead into a fun unit, so don't worry. Might be a little boring at first, but got to get through the history to understand why we know what we know. So, starting with elements. So, elements are like the purest form of a substance that cannot be decomposed by chemical change. So, we can't break them down any further in the sense of how something reacts, right? But we can pull apart our elements and look at them at a tiny, tiny scale in thinking of elements being made up of atoms. So atoms are truly the smallest piece of an element where they still retain those properties of the element. So the properties remain the same. So let's talk about what makes up an atom. The first of which are protons. And so protons, good thing we covered scientific notation, because get ready for this, their mass is 1.66 times 10 to the negative 24th grams. That's tiny. A paperclip weighs about 1 gram. This would be like 0.0000000000000 all the way till we get to negative 24, right? And so instead of referring to it as that many grams over and over, we're going to label this amount, we're going to call that 1 atomic mass unit, or AMU. The proton has a charge of positive 1, and where we say it's located is inside the nucleus. Then we have our neutrons. They have the exact same mass, so they also weigh 1.66 times 10 to the negative 24th grams, but we know that as 1 AMU now, so protons and neutrons weigh the same. How they differ is their charge. Neutrons don't have a charge to them. That's why they're called neutrons. They're neutral. They are also located inside the nucleus. So these two subatomic particles, these are what make up an atom's mass. Because these are the only two out of the three that have a mass to contribute. And so we'll talk about isotopes. What isotopes are? They're atoms of the same element with different, I'm going to shorthand number with a little number sign here, of neutrons. We're going to talk about why that's how isotopes are, why it can't be protons. And so the third subatomic particle that you guys have to know about are electrons. And so if we are thinking in terms of AMU, the mass of an electron would be 1 over 1,836 AMU. So that's tiny. So divide that 1 AMU by 1,836. So in the world of chemistry, we say that the electrons have no mass. And so we're going to label that as 0 AMU. They don't affect how our atoms interact. They don't have enough mass to, so we just say it has nothing. The charge on the electron, however, is -1. And where we define these electrons, their location is not inside the nucleus, but orbiting around it, just like the planets orbit the sun. So they're orbiting the nucleus. Now, electrons are important. They practically rule the world, which is what you're going to end up finding out after the next couple units here. But they can also make us have ions. So ions are atoms that end up having a charge, so they're not neutral anymore because of the number of electrons. So, how do we figure out how atoms are different? Well, it has to do with the number of each of these things. So we have to first talk about a few definitions, the first of which is the atomic number. So what the atomic number tells us is the number of protons. This is how the periodic table is ordered, is by how many protons these elements have inside the nucleus of their atoms. And so what you'll notice is on our periodic table, well, on all of them, they're a whole number, but on the periodic table up on the wall, it's the blue numbers that we have. That's not always the case. The reason why this is so important is because the number of protons, this is what establishes the identity of the element. So, if we start changing the number of protons, we're changing the identity of our element, right? So, when we think back to our isotopes, we know that isotopes have different masses, but the reason why their masses change only on neutrons is because if we start changing the number of protons, then we're not working with the same element anymore. So that's why neutrons differ and protons don't. So, in terms of our mass number, we discussed that electrons are practically massless, so the only two things that go into our mass number are going to be the number of protons added to the number of neutrons. So this is going to be an equation that you guys are going to want to be familiar with. Is that mass number equals number of protons plus number of neutrons. And so, again, this is a whole number. And the reason why I'm emphasizing this is it is actually not the mass that we're familiar with on the periodic table, which I'll just shorthand as PT. Stands for periodic table. Okay? So, what mass number is mass of a specific singular atom. What we see on the periodic table with decimals is an average of all the naturally occurring atoms. So atoms, again, don't have to have the same mass. That's why we have this term called an isotope. And so on the periodic table, it's an average of all those different isotopes, but the mass number is of a specific singular atom. And so we can't figure out how many neutrons we have unless we have the mass number. That's the only way. So to get the number of neutrons, we just rearrange this equation. So if you were in algebra trying to solve for number of neutrons, you have to get number of protons away. Well, you subtract that from both sides. So our number of neutrons is equal to our mass number minus number of protons. So this would be like another example of an equation that you guys should be familiar with. So when I refer to an atom, I mean that the particle is neutral. And so what I mean by neutral is that the charge has to be equal to 0. Well, if the atomic number is the number of protons, those are our positive charge, well, our number of electrons, which is our negative charge, better equal our number of protons then. So when we are figuring this out, you guys can assume that the atomic number is equal to the number of electrons as well. So what I have to teach you before we can work with identifying and distinguishing subatomic particle quantities is what's called the nuclear symbol. So this is going to have two numbers to the left of the element symbol. The top number is going to be the mass number. The bottom number is going to be the atomic number. So the atomic number you can get off the periodic table. I either have to give you the mass number or the number of neutrons, or else we can't have that, okay? So again, this is not off the periodic table. So what I want us to do is practice writing the nuclear symbol for this atom I have pictured up here. So this is a carbon atom, right? Let's say I didn't know that, it wasn't labeled. Well, I would count how many protons there are, and that's equal to the atomic number. So I would go to the periodic table. I would look up what is number 6. So if I zoom in here, it's not a very good table, but you can see that carbon is atomic number 6 right here. So I'd be able to see that it's carbon I'm working with. So, oops, I accidentally put 2 on here. So I know I'm working with carbon now, so I'm going to write that as my symbol. Then the top number is my mass number, and the bottom is my atomic. Well, I just figured out that atomic number is protons, so I know that the bottom number is going to be 6. And so in order to calculate my mass number, well, mass number is equal to protons plus neutrons. Right here I say I have 6 protons and 6 neutrons. So I'm going to add those numbers together and put it here. 6 plus 6 equals 12. So that would be the nuclear symbol of carbon. So you don't have to put the boxes there. I just like to show you that while we're learning. So the next thing we're going to do is go through some of our beginning elements and work through figuring out how many protons, electrons, and neutrons we have. So recall that our mass number is going to be equal to our number of protons plus number of neutrons. Okay? So let's start with hydrogen. Hydrogen, if you look up that element on the periodic table, its symbol is H, and it has an atomic number of 1. So we can right away place this atomic number where it goes in the nuclear symbol. We also know that the symbol, or the number on top, is going to be our mass number, which is 1 in this case. That's going to be the number above. So we're done with our nuclear symbol. Now we can fill out the rest of our information. Number of protons is equal to our atomic number, so we put a 1 there. We assume all of our atoms are neutral, so that'll be the same number of electrons, again making sure that our plus charge and our minus charge cancel. Now, to figure out the number of neutrons, again that is equal to our mass number minus our atomic number, or our number of protons. So if we take our mass number, subtract our atomic number, that means we have 0 neutrons present. All right, let's do another one. Helium, symbol He, its atomic number 2, so we can right away fill in that we have 2 protons and 2 electrons because it's neutral. We can also fill in the bottom number of our nuclear symbol. We can place our mass number on the top of our nuclear symbol for, I apologize, or my cell phone vibrating. And then we just have to figure out our number of neutrons. Well, again, it's our mass number, which we were just told was 4. And we subtract off our atomic number, so 4 minus 2. So we must have 2 neutrons present. For lithium, symbol Li, this is atomic number 3. So I can place that in the bottom of our nuclear symbol. We have 3 protons and 3 electrons then. We can place 7 on the top because, again, mass number is the top number. And then I want to teach you a trick of why we use nuclear symbols and why they're so awesome. And the reason being is, okay, how do we figure out the number of neutrons? That is mass number minus atomic number. Well, look how it's set up on your nuclear symbol. What you have is the mass number and then the atomic number below. So you can truly just think of it like a subtraction. So if I were to think of it as I put a line here and subtract those 2 numbers, 7 minus 3 equals 4. That's our number of neutrons. So you can use that trick when you are calculating number of neutrons. Next we have beryllium, Be, atomic number 4. So we place 4 for our atomic number, 4 protons, 4 electrons. We place our 9 on top. And again, if we do that trick, 9 minus 4 gives us 5 neutrons. Boron, number 5. So getting a little repetitive here, which I'm hoping it will be as we're getting the hang of it. Mass number 11 goes on top. 11 minus 5 gives us 6. And lastly, carbon here. If we have a carbon, atomic number 6, that means we have 6 protons, 6 electrons, so it's neutral. And our mass number is 12, goes on top of our nuclear symbol. 12 minus 6 equals 6. So at this point, what I want you guys to do is fill out this chart on your own. And so I did it more like a puzzle to challenge you a little bit. I want you to either use the mass number to figure out the number of neutrons, or if I give you the number of neutrons, let's see if you can figure out the mass number. Remembering that mass number is protons plus neutrons. So if I give you neutrons, you have to figure out your atomic number, therefore your number of protons. So truly, to get the mass number, you're adding neutrons plus protons.